Okay, so we've talked a little bit about molecular orbitals, we've talked about electronegativity. So in both of those topics, we've talked a little bit about what makes a covalent bond. So just as a quick review, from mode theory, we said that when you form a sigma bond, for example, the greater the overlap and energy matching, so these two examples were here. So overlap, matching energies is what makes a stronger covalent bond. And what we talked about before was that, so for example, dihydrogen, the two 1s orbital energies are identical, so then it forms a very covalent bond because they're the same energy. In contrast, HF, because the fluorine positive charge of the nucleus really stabilizes that 2p electron, then overall this energy matching is not so good, and then so the covalency of this bond is less. From electronegativity arguments, we know that, if this is big, it's more polar, ionic, and then if we were saying that delta chi is small, then it's more covalent. And then so from these two kind of different models or ways of thinking about covalency, you can see that they're actually the same, which is that, right, big differences in electronegativity are energy matching of the orbitals is going to be poor. So that's the kind of general concept of covalency, like how readily that they share, how equally they share the electron between the two within the bond. But I wanted to talk about one more aspect that you can think about for what makes a bond covalent in a more, let's say, a more polar molecule where we do have differences in electronegativity. Like, how do we compare covalency between two different types of kind of heterodiatomics that already have different electronegativities? Oops, let me quickly erase this. So one thing to consider, if we're no longer thinking about just electronegativity and the MOs, is the concept of charge density. And then that's defined as, for let's say an ion, as Z over R. So this is for an ion. For an ion. And then so here, Z is no longer big Z, which was the nuclear charge. We're talking about little z, which is the charge of the ion. So for example, sodium plus is Z equals +1. And then here would be the ionic radius. So here we're talking about a charged ion, and then how charged that is depends on how big it is and also how much charge it holds. And then so the reason I want to talk about this is because the charge density of a cation or of an anion really affects the covalency of the ultimate bond that it forms. So here's one example. So suppose we have, let's say, lithium plus versus magnesium 2 plus. So these are related by that diagonal effect, so they're actually quite similar in terms of charge density. But let's just talk about how we kind of calculate that. So this Z equals 1 because it's monocationic. Magnesium is Z equals 2. And then so overall, this has a higher Z. And then if we look at the size, in this case, they're actually, let's see, I don't have full on numbers, but this is the Z that we're using. So magnesium is going to be slightly bigger. So then overall, that Z over R, that's how we get to a similar charge density. So anyway, Z over R, that's charge density. Keep that in mind. So the effect that it has on bonding is, let's talk about lithium chloride versus potassium chloride. So lithium chloride, lithium chloride has, let's say this is our lithium cation, so it's going to be quite small. And then chloride anion is quite big. It's bigger because we have an extra electron, so chloride is big. And then for here, our Z equals 1. Oops, Z equals 1, right? And then if we compare it to potassium chloride, potassium is 2 down from lithium, so it's going to be much bigger. And then we still have Z equals 1. And then here we still have chloride. So the reason this has an effect is if we think about Z over R, let's see. So Z over Z, they're both Z equals 1, but R lithium is much, much smaller than R potassium. And then so what we're saying is the charge density, which is, again, Z over R, Z's are both the same, but it's inversely proportional to the ionic radius. So because this is smaller, the charge density of lithium is much higher. Density right, Z potassium over R potassium. So that's just it. So lithium is more charge density. And then so this is what we call, this lithium ion is more polarizing. Polarizing. A cation with a high charge density, meaning it's either small or very highly charged, right? To make this big, you want either a high Z or a small r, or both. And then you get a high charge density, so it becomes polarizing. So what it means to be polarizing is that it can move electron density towards itself. So when you have this lithium small point charge and you have your electron cloud of the chloride, it kind of distorts this big fat diffuse electron cloud towards itself. And then so what you end up with is something like that, right? So that point charge can pull the electron away from the chlorine. And then so because of that, by distorting the electron cloud towards itself, the lithium can share the electron density of the chloride better. So this is going to be more covalent. In contrast, if you think about the positive charge of potassium, it's actually rather diffuse. So because it's not small, it's kind of, this chloride feels it all rather equally. So it doesn't polarize. So then you still keep it like this. So then we have positive charge, negative charge, and therefore it remains kind of intact as separate ions. So this would be more ionic. So again, cations, okay, so the kind of takeaway point I want to have is that small cations, small, highly charged cations, sorry, that's running out of ink. These are polarizing. And then when they interact with big, kind of like low-charged anions, let's say big fluffy anions, these are called polarizable. And then so when you have a small, highly charged polarizing cation interacting with a polarizable big anion like chloride or even more iodide, then we can form a more covalent bond than if we have, lower charge density on the potassium and the chloride. So kind of the take-home point is that because lithium chloride is more covalent, it's actually more soluble in nonpolar solvents. So lithium chloride is very soluble in THF. Potassium chloride really isn't because it's more ionic. We'll talk a little bit more about solubility in water later because that gets even more complex. So don't worry about solubility in water, but just think about the more covalent you are, the more soluble you are in nonpolar organic solvents. Okay, so polarizing, polarizable. Don't get this mixed up. Polarizing means that it's small, highly charged. Polarizable is big, and typically an anion. Another term for small, highly charged, and polarizing that we'll get into in the transition metal part is small, highly charged cations and anions are known as hard. And then big things that are less charged are also known as soft. And then that kind of makes sense, right? Soft is polarizing, or polarizable. You can kind of easily, change your electron cloud density. It's somewhat similar to the London dispersion forces you might have seen before in high school. And then hard is going to be small, highly charged. It's not very, like that whole orbital situation is not going to move around very much. Okay, so covalency, there's other aspects to it that might be easier to picture. Again, this does not negate what we talked about with electronegativity, right? Electronegativity, lithium and chloride are still a smaller delta chi than potassium and chloride. But this is another way to think about, effects on like what covalency actually means.